Quantum computing leverages four key principles. Superposition allows qubits to exist in multiple states simultaneously. Entanglement links qubits together. Interference amplifies correct solutions. Measurement collapses the quantum state to reveal the answer. Moving on. Quantum algorithms exploit quantum mechanics for computational advantage. Shor's algorithm can factor large numbers exponentially faster. Grover's search provides quadratic speedup for database queries. Quantum annealing solves optimization problems. Quantum machine learning accelerates pattern recognition. Moving on. Quantum computing has three layers. At the top, applications like drug discovery and cryptography. At the bottom left, algorithms that provide quantum advantage. At the bottom right, physical hardware implementations using superconducting circuits or trapped ions. Moving on. The fundamental difference lies in the bit. Classical bits are either 0 or 1, operating deterministically through simple logic gates. Qubits exist in superposition of both states simultaneously, operating probabilistically through quantum gates that manipulate probability amplitudes. Moving on. Quantum computers promise breakthroughs across industries. Cryptography will be revolutionized, requiring post-quantum security. Drug discovery benefits from precise molecular simulation. Finance gains better optimization. Materials science can design novel compounds. Machine learning gets quantum acceleration. Moving on. Quantum error correction is essential for practical quantum computing. We encode logical qubits across multiple physical qubits. Continuously monitor for errors without measuring the quantum state directly. Correct detected errors. Then continue computation. This cycle repeats thousands of times per second. Moving on. Building a quantum computer requires three critical subsystems. Qubit fabrication creates the quantum processors with minimal defects. Control electronics generate precise microwave pulses to manipulate qubits. Cryogenic systems cool everything to near absolute zero. Only when all three achieve sufficient quality does the integrated quantum processor function. Moving on. This equation describes quantum superposition, the foundation of quantum computing. A qubit isn't just 0 or 1, psi represents but a complex the combination quantum of both states simultaneously. Alpha is a complex number whose magnitude squared gives the probability of measuring 0. Beta is a complex number whose magnitude squared gives the probability of measuring 1. These are the classical 0 and 1 states, the basis vectors of our quantum space. Moving on. Here's how to create a quantum circuit that demonstrates superposition and entanglement using IBM's Qiskit framework. Let's create a quantum circuit using Qiskit. We create a quantum circuit with 2 qubits and 2 classical bits for measurement results. The Hadamard gate puts the first qubit into equal superposition of 0 and 1. The CNOT gate entangles the 2 qubits, creating a Bell state where their fates are linked. We measure both qubits, collapsing the quantum state into classical bits. We run the circuit on a quantum simulator 1000 times to build up statistics. The results show both qubits are perfectly correlated. We only see 0, 0 and 11, never 0, 1 or 10. This is quantum entanglement. This demonstrates quantum superposition and entanglement in code. Moving on. This graph shows qubit decoherence. The oscillating wave represents the quantum state, while the exponential envelope shows decay due to environmental noise. The coherence time T2 determines how long we can maintain quantum information. Longer coherence enables more complex quantum algorithms. Moving on. This exponential curve shows quantum computing's power. Each qubit doubles the quantum Hilbert space. While a 10-qubit system is classically simulatable, for small problems with few qubit system exceeds all computers are faster due to lower overhead. This exponential scaling around is quantum 50 to 100 fundamental advantage. Quantum computers reach quantum supremacy, matching classical capabilities. Beyond this point, quantum advantage grows exponentially. Each additional qubit doubles quantum computational power, while classical simulation becomes exponentially harder. Moving on. Developing quantum algorithms is an iterative process from problem formulation through hardware execution to result analysis. Start by clearly defining the problem you want to solve and why quantum might help. Analyze the classical algorithm complexity to identify potential quantum speedup opportunities. Design a quantum algorithm that leverages superposition and entanglement. Implement the algorithm as a quantum circuit using available quantum gates. Validate correctness on a classical quantum simulator before using real hardware. Execute on actual quantum hardware, accounting for noise and errors. Apply error mitigation techniques to improve result quality. Analyze results and iterate on the algorithm design based on performance. This pipeline bridges theoretical quantum algorithms and practical quantum computing, requiring both quantum physics expertise and software engineering skills. Moving on. Quantum gates transform quantum states through unitary operations. The gate U is a unitary matrix that preserves the normalization of the quantum state. Unlike classical gates, quantum gates are reversible and preserve quantum information through unitary transformations. Moving on. Quantum entanglement is perhaps the most counterintuitive feature of quantum mechanics. Einstein called it spooky action at a distance. It's what enables quantum teleportation and many quantum algorithms. Quantum bits that can exist in superposition and become entangled with other qubits. The measurement outcomes are statistically linked in ways impossible for classical systems. The act of observation that collapses the quantum state and reveals classical information. Entanglement persists regardless of spatial separation, though no information travels faster than light. Entanglement is a resource in quantum computing, allowing operations impossible on classical systems. Moving on. 1981, Richard Feynman proposes quantum computers to efficiently simulate quantum physics. 1994, Peter Shor discovers quantum algorithm for factoring, threatening modern cryptography. 2019, Google achieves quantum supremacy with 53-qubit Sycamore processor. 2023, breakthrough demonstrations of quantum error correction surpassing the break-even point. Moving on. Quantum computing leverages quantum mechanics for computational advantage. While current systems are noisy and small, rapid progress is being made toward practical quantum computers that will revolutionize computing. Thank you for watching. You can generate other tutorial videos with our platform.